So welcome to the second part of this revision of the chapter 5 current mirrors, and in this video we'll specifically deal with active current mirror or differential pair with active load, or we can call it a 5 transistor OTA, which is basically operational transconductance amplifier. So this is the basic idea that for a differential circuit we can have active load, and we are it's not technically correct to call it active load, but anyways, basically we what we are doing is basically that we are using transistors as our load for the differential pair. And so this is the basic configuration. We need to decide certain V bias so that they can act as a load of suitable value. For example, if I'm making it function as a current source load, let us say, so my V bias value should be such that these two guys are working in saturation regime. Now, one way to bias these two guys, because we want ideally that the bias current of I that the bias current, or half the bias current of the tail, flows through each of these branches. So we can, one way to bias is that we can use a current mirror only, and we can say that, let us say that this current is of the value IRF by 2, and we are mirroring it in these two transistors. But now if we observe really, we can understand that since here W by L is same, here W by L is same, here W by L is same. So basically I can say that I can basically bring this transistor straight away right here only, right? And I can just because fundamentally I want that these two transistors operate at saturation, carry IRF by 2 current, and since everything else is symmetric, so I can just bring this current, this IRF branch over here, and I can basically just diode connect this transistor, and then this final circuit that we obtain is called 5 transistor OTA, or trans conductance amplifier. So this is the final circuit that we obtained, and what it is basically doing is that it is taking the difference of these two signals, and it is like basically a single-ended amplifier in a way, since we are only taking output at one of the ends and achieving a subsequent result. I think we already described this in chapter 5, chapter 4 revision of differential amplifiers, that why we typically use single-ended amplifiers. And as we'll discover down the line, as compared to a basic single-ended differential amplifier, the gain of a two-stage OTA is basically double. If you recall, the gain of a single-ended differential amplifier was of the order of GM RD by 2, but here we'll find that it is of the order of GM times RD. Great. Now let us discuss some properties of this differential amplifier. So first of all, let us discuss its large signal analysis. So here, if I'm defining my difference of input voltage as V1 minus V2, which is basically the difference of V1 minus V2, which is shown over here. So if I keep on increasing V1 with respect to V2, that is my V1 minus V2 value somewhere around here, which means very high. So my ID1 will increase and my ID3 will increase since it is in series with this guy. And so since current is being mirrored from M3 to M4, my ID4 will also increase, correct? But now we should observe that my I bias is fixed. Since my I bias is fixed, my ID2 current will decrease because my ID1 current is increasing. Now, the fundamental doubt that comes into picture over here is that since these two transistor in series, then these two currents must be the same. That's the kind of doubt we typically tend to have. So the basic idea here is that there is an inherent node capacitance associated with this node V out. And so what basically happens is that when either of the two currents is larger than the other, this capacitor charges or discharges accordingly. Okay. So this was the doubt which also troubled me for quite a long time. But now this is the basic idea of philosophy behind analyzing such kind of circuits, when we are saying that two transistor series have unequal currents. So this is the basic thing that is happening there, that the node capacitance just starts to charge or discharge. Great. So in large and anyways, these are large signal analysis, and in small signals, okay, so that is a talk of later, but yeah, that is the basic idea of the node capacitance at V out. So what's basically happening is that when V in is too large, so ID1 will increase, which means ID3 will increase. So now you can also say that there should be some node capacitance over here. So why is there no mismatches or that sort of thing happening over here? So that is again a valid doubt. And to be honest, I don't have a clear-cut explanation for that. But what I can say here is that if ID1 is increasing, the node capacitance over here is less as compared to node capacitance over here. And why am I able to say that? See, the capacitance over here will be some parasitic capacitance, right? And that parasitic capacitance will be a way, way smaller value. That means it can't charge or discharge that much. But here you would also have some load capacitance which can charge or discharge by a great amount. So that is an explanation that I have, but although that's not great, but we analyze it anyway. So ID1 is equals to ID3, and because bias current is fixed, so ID1 plus ID2 must be equal to I bias, which means ID2 will decrease, which implies that at this particular node, since ID2 is less than ID4, this implies that this capacitor will effectively charge, which means that the node voltage at Vout will increase, right? And at extreme case, when ID2 is 0, we can say that this Vout can charge up to VDD. Great. And eventually, as this difference decreases, so will the node voltage at V out, and we'll have this kind of a behavior, and eventually it will achieve arrive at the zero value. So this is the last analysis, and why it is zero here. Let's again analyze an extreme case. So here V1 will be zero, and V2 will be very high, and because of this, all the current will flow through ID2, and since all the current is flowing through ID2, and here zero current is flowing, here zero current is flowing, here zero current is flowing because of mirroring, which implies that all of this capacitor will be discharged fully. And since this node voltage just can't go to negative, it will just discharge. It can actually it can it go to negative. If you just see that the supply rails here are, I'll just confirm that, and it should not technically drop down to negative values. And yeah, as I expected, it won't drop down to negative values exactly. So it will just drop down to zero because here supply rails are VDD and zero. So this capacitor will discharge until it attains a value of zero, and thus our Vout eventually will reach a zero value for high V2 and small V1. Basically, V1 minus V2 is a very negative value. This was the large signal analysis. Now, for the small signal analysis, since it's a revision, we already know that the effective R out of this 5 transistor OTA is R naught N parallel R naught P. Although we should understand that it is not straightforward saying that here transistor, here is this R naught and here is this R naught N, and so we took parallel. It was not like that. How we basically found the output resistance of this guy was that we first said that let us just draw this 5 OTA first. I'm not deriving it for thoroughly, but I'm just trying to get at how we did that. So we just applied a V-test here, and I detached it, and I said I'll apply some V-test over here, and I'll find this resistance, and I'll find this resistance. Okay, one at a time. So what I mean to say is that we are trying to first apply a test voltage here, same test voltage here, then I'll see that what is the resistance seen through here and what is the resistance seen through here, and then I'll effectively take that parallel and I'll achieve at my result. Okay, so that the process goes like this. It is not that since at output there is one PMOS and then one NMOS, we will directly saying R naught parallel to R naught P, but it's a good way of remembering, but we should keep in mind that it was not how we derived it. That out of the way, the effective GM approximately turns out to be equals to GM1 or GM2, basically the transfer conductance of either of these two transistors, and thus the gain is of the order of GM times R naught N parallel R naught P, right? Which is quite a high gain if you compare it with a single-ended differential amplifier. So that's the basic idea. If you still can't appreciate the fact that why it is double of a basic single-ended differential amplifier, I can just draw this guy. Let us say that is VB, and this VB voltage is such that basically the resistance that both of these guys are in saturation, and I'm just saying that they are offering resistance of R naught P, R naught P, R naught N, R naught N, and this is the differential input pair, and we are just trying to find the gain. Okay, and since here there was a current source, so we can basically open this guy, and so the transconductance, if you try to find the transconductance and the gain, so the idea is pretty much the same, only that you are saying that guy will function as a load, this guy function as a load, so our output impedance happens to be R naught N parallel R naught P. But when you talk about the transconductance, you will find that it is GM by 2, and thus you can say that the gain is typically double of a simple single-ended differential amplifier when we are talking about a 5-stage OTA. So that is also one of its advantages. So yeah, so this was the small signal analysis for differential gain. What about common mode gain? So let's also talk about the common mode gain, and we can already appreciate this fact, and I think I should also mention this somewhere, that this 5 OTA is asymmetric, as we can already see. It's a fundamentally asymmetric circuit, but for common mode signaling, where I'm applying same signal here and here, it is behaves symmetrically. Although physically it is not a symmetric circuit, and let us try to understand this point also. Okay, let us try to understand this point also. So the thing what I'm trying to convey over here is that if or I'll just try to show this on this circuit only, that how is the circuit behaving symmetrically. Say that VCM and VCM, they both increase by the same amount. And let me say that here my I1, let us say, is more. Or let us say that why I'm saying the circuit symmetric is if I'm increasing both these node voltages by same amount, and if this circuit is symmetric, that implies that this node voltage and this node voltage are same. And if these two node voltage are same for common mode, then I can say that I can basically effectively short these two guys, and I can basically fold this five-stage OTA as you were doing in a fully differential amplifier. Let us try to test whether this is true by just trying to by contradiction. We'll try to prove if this thing is true or not. So yeah. So if you're saying that, let us say that Vx is more than Vy, for this NMOS pair, it will basically implicate. What will it implicate? If Vx is more than Vy, what will it implicate for the NMOS pair? If Vx is more than Vy, then what will it implicate for the NMOS pair? Like which current will be more? I1 will be more than I3, or I2 will be more than I4, or like there are combinations here with respect to the current magnitude. So what can we basically say? So what we can basically say here is that that if Vx is more than Vy, if for this for NMOS perspective, we can basically say that I1 will be more than I2. But from PMOS perspective, if Vx is greater than Vy, we can say that since Vx is a large value, which means the drain to source drop here is less. Again, here we are saying this on the basis of channel length modulation. Remember that, because VDS term also multiplies to the current, right? So here I'm thinking that way. So for from PMOS perspective, the VST will be of a smaller value, and that will basically imply that, which basically implies that I3 is more than I4. But here PMOS will say that I3 should be less than I4, which implies that I2 must be more than I1. So by this contradiction, we can say that the only possibility that we have is that I1 is equals to I2, and I1 is equals to I3, and I2 is I4, which implies that Vx has to be equal to Vy. So this is the contradiction by which we are saying that five-stage OTA is a symmetric circuit, right? And now let us just try to analyze the circuit for common mode. And now we already established, since this circuit is symmetric, I'll just fold this guy, and I'll just write it this way. Twice of GM, and here also the distance that we are effectively able to see from this end, this is V out, and from here we'll be able to see what? Twice of GM, and I'll call it GMP, GMN. And if this, I'm considering some tail resistance, so it is Rx. So you can understand that for an ideal tail current source, this guy will be basically infinite, and that means that the common mode gain will be zero, because the small signal current won't be able to flow. But here we can just easily conclude that the common mode gain here will be inversely proportional to Rx, which means that higher the value of Rx, or more ideal the tail current source is, the better or the lesser the common mode gain will be, right? So that out of the way, we are able to describe what a common mode will look like. And let us now fundamentally now discuss the advantages and disadvantages of five-stage OTA. One is that despite being a single-ended differential amplifier, the gain is basically twice of that of a basic single-ended amplifier. Also, that it basically merges the bias current of the loads into itself, and so it basically consumes lesser power. right? As compared to a basic differential amplifier. But the disadvantage over here, and there's a fundamental disadvantage, is that its common mode rejection ratio, CMRR, rather, is finite despite perfect symmetry, and that its power supply rejection ratio is also poor. So, the main idea here is that what we are trying to convey is that we saw in fully differential amplifiers, what we saw there was that when there was a kind of a mismatch, we were finding there was a con mode to differential mode conversion, right? And we were taking basically output as difference of these two nodes, but we can kind of understand that when there was some variation in common mode signal, and when we are taking only single-ended response, so there the common mode differential conversion was uh, there, right? Can we say that it will be there? I think we did not discuss it, but the main idea was that in a fully differential amplifier, the common mode to differential mode conversion was happening only in case of mismatch. But what we are saying here is that in a five-stage OTA, despite perfect symmetry, the common mode to differential mode conversion will be a finite value, which is quite a problem, right? So this is one of the disadvantage, that common mode to differential mode conversion is always finite despite perfect symmetry, right? This is one of the disadvantages of five-stage OTA. And I think we'll try to look into this deeply in the next video. And also, with this, the five-stage OT is very quickly wrapped up. And one more thing that we might explore if we have time is that how is the common mode rejection property of a single-ended differential amplifier? That is also something that we will try to look into. And after that, we'll only be left with last topic, which is the biasing techniques. And if time permits, I'll also just go through this one example of a high-sync cascode current mirror. So that was the video, and I'll see you in the next video. Thank you.